Okay, we're back and ready for our next talk. We're going to get deep into mobility. Esteban has joined us. Hello, Esteban.
Hello, thank you for this invitation, for this great opportunity to talk about our work. Thank you for that, and that for Regina also.
It's going to be great. I'm looking forward to it. I've been living my life in a fog of darkness, not knowing enough about mobility DB. So this is my chance to get put straight. Why don't you take over the screen share?
Let me know.
How you want to work? Switch. Of course it will. It usually hides down at the bottom, the middle.
So what should we share screen green?
That's the one. Click the share screen button, and now you are sharing.
Is it okay for everyone?
It's good to go.
Okay, thank you for this. I will be talking about a general architecture of mobility DB. I had the huge opportunity to have a detailed talk about mobility DB by Wendell right after that. So I'm giving an overall view of all the architecture we have been building to make mobility data, to enabling mobility data in multiple computing environments. So what type of mobility data we are talking about? Of course, the position, latitude, longitude, and timestamp, which in mobility DB, there are two data types for that, the geometric points and temporal geometric point and temporal geographic point, depending on whether you are, these are the equivalent of geometry and geography in PostGIS. Then we have the speed, which is, of course, a float that evolves on time, for which we have a temporal float. Then we could also want to decide, determine whether this car is going above the speed limit of the road. And then this is a temporal Boolean, which can be sometimes yes, sometimes not. And the gear, it's also a temporal integer, 1, 2, 3, 4, 5. And at each point in time determines which is in which gear the car is going. And finally, we can also have like a highway primary. This categorization that comes, for example, from OpenStreetMaps, where you can say at this point in time, the car was running on a highway or on a primary road, etc. So this is a temporal text. And let's see how this data comes into reality. So this is a real data set from a real constructor, well-known constructor, car constructor, and then they collect the data. Look at this at every 10th of a second, and we are having here 2,000 signals. So it's a huge table with 2,000 columns, and imagine all cars of this constructor manufacturer traveling in Europe. It's sending this data, this huge data set, to the headquarters here in Brussels in order to collect and do an analysis of this data. So what we can see about this data is that this data is very redundant. We have here the moving state, whether it is the motor is on or off, and imagine doing this only for every 10th of a second. So this is not very efficient. A way to compute that in mobility DB, or to store that in mobility DB, we use delta compression. We only need to keep the instance in time when the value change, and then if there is nothing, then we continue with the previous value. So we can have the same of a temporal flow. This is the speed. And so each of these temporal signals, we will represent it as a temporal data type in mobility DB. Let's go. So this is the original data when we're talking about location. So we have latitude and longitude here. And what mobility does, using exactly the same data, is to connect it. We know that this is coming from a data, and then the data is connected. One point is connected to the other. So it's already, without doing anything, the mobility DB knows that this data is connected. And then, for example, we can ask at where is the location a particular timestamp, which is, for example, between two observations. But this is a very nice thing already. But what we need to understand is that this data, even like this, only considering the evolution of the location of the car, there are many redundant information. Suppose here that there is a traffic light, and then during 1 minute, this car is telling every tenth of a second, I'm at this location, I'm at this location. So it's useless to have this set of points, set of observation here can be just compacted into two. One when it was arrived to the red light, and then second the other one when we start driving again from the red light. Again, if we think here at this very straight line, if the car is going in the same speed and the same direction, all these data points in the middle are not necessary. Basically, we can remove all the intermediate points, and then we have only the points that are necessary without losing any data. So basically, we have a lossless compression in which MobilityDB, as soon as we are entering data, determines which of these observations are not needed and can be deduced from the observations that are kept into the temporal geometric point in this case. So going back to our original data, we have this, even if you have it in, for example, Parquet format, so but it's a line-oriented, record-oriented representation, which is redundant. MobilityDB uses the temporal types inside each row. So here we have one row for all these 16,000 records, where each of the moving parameters or each of the temporal parameters are in a temporal data type. And for example, the gender or the age of the driver are traditional attributes. So here we know that there is a huge compression rate that already we performed using this data. So the most ineffective algorithm you use to processing this data, you use exactly the same algorithm in the two representations. The one in the hour representation in MobilityDB will be 400 times faster, just because we are having less data. But of course, see now that we have a much compacted representation, we can do binary search, and more optimizations can be done on this data. We did that, but also the public transportation of Moscow did that many years ago. So our first public presentation of MobilityDB was in Russia in 2019. 1 year later, we came back to Moscow to do the presentation, and we discovered when we were registered at this presentation, at this conference in 2020, that public transport of Moscow, after our speak 1 year later, implemented this into production, and then they obtained similar kind of compression, lossless compression, when, for example, here we have 30 gigabytes per year in the tabular format, where in MobilityDB we have 2 gigabytes per year, which is much efficient to process. So in essence, what we have with MobilityDB, we have a compact data storage with lossless high compression rate. Of course, this implies a query speed up, and it's compatible with full Postgres SQL ecosystem. Of course, we have interpolation, native mobility or time-based data type, a lot of analytics. Wendell in the next talk will explore many of these functions. And of course, it is a huge development in reduction in development time. We will see an example in a couple of slides. So this is another example that we have just a bus that goes here in front of our university, and then this goes beyond, it goes in front of some billboard advertising, electronic billboard, and we want to compute the time when this bus is less than 30 minutes from 30 meters from the billboard, to a little bit assess, given how many people are in the bus, how many people were seeing that particular ad. So if we want to do this in simple PostGIS without time, Basically, these are our original observations. We have one observation in the blue for one bus and the other observations in red for the one bus. And these are the examples of the billboards. And if you want to do the same only in PostGIS, we need to basically connect the dots. And then connecting the dots is something like this. We first need to use, for example, a window function to get one point, one location, one observation with the next one, using, for example, the lead function. Now we have one point and with the next point in the trajectory. Then in the next CTE, we connect these two with a line. And then in the third step, we put a buffer of 30 meters around the billboard, and at the end, and verify whether this STD within the distance of the bus with the boundary is less than 30 meters. And at the end, we need to determine the time when this advertisement was, people inside the bus were seeing this advertisement. You can imagine that writing this code, which is basically connecting the points, every time you need to do manipulation of this in spatial only system, it's first difficult to express and also very difficult to optimize. In MobilityDB, we have already this kind of thing, exactly the same thing. We assemble the trips, which are the blue and the red trips. We have the billboards. MobilityDB knows that this is a moving point, a temporal point. This is a fixed point. We determine whether it is the case that this is a Boolean predicate. It is the case that the bus passed ever along this trajectory within 30 meters. So here, for example, this binary predicates, Boolean predicate throws away the red line because it was never close to the billboard. And then after, when we selected the couples of bus and billboard, we can define, give me the points in time whether this bus was within 30 meters of the billboard. So we see that if comparing this with this, it's a much more easier way to write code when the MobilityDB stores in the same way as PostGIS will do it, but we know inside the system that the points are connected, and we take into account the semantics of the temporal aspects without forcing the user to write the semantics. A similar example, but now with two moving points. These are two ships, real ships in that date, in 2018, that traversing a canal in Denmark. So we are computing the time, the instances time wherein these two ships were less than 100 meters to each other. So this is a near collision detection that is very important for ships. Again, the query is exactly the same, written the same word. So now it will be ships A and ships B. MobilityDB will know that the two, we are talking about two moving points. And then with the same queries, we replace 30 by 100 here. And then we can obtain exactly the same thing. So this is the beauty of MobilityDB, that takes into account time, and then you don't need to, or provides all the analytics for time-related functions. So MobilityDB is open source. You have here on the left the GitHub of the repository. It has been approved by OSGeo a few years ago, and we have, in addition, the huge chance to be involved in the OGC standardization committees for moving features, in the same way that OGC edited the standard for static features, on which PostGIS is based. So my colleague Mahmoud is co-chair of these moving features, and so we collaborate really with them continuously to develop the new standards for moving features. From an architectural viewpoint, if we can see here We have Postgres, which provides data types, Boolean, numeric characters, JSON, and operations on top of that, and then indexing on top of that, and then statistics for determining the for query optimization. On top of that, of course, PostGIS added the two data types, geometry and geography, and the bounding boxes, of course. And then on top of that, we provide all the thousands of functions that you know very well available in PostGIS, and then extended the indexing and the grid-based statistics for query optimization. On our side, we take into account only time. Let's put it in this way. We need to delegate the geometric processing to PostGIS, whatever alphanumeric processing to PostgreSQL. So we delegate all this processing to the underlying base type, and we determine at which point in time we need to call PostGIS or for a nested distance operator. In the case of our two ships over there, we need to be smart to define at how many times we are sending the distance query of two moving ships in order to be efficient. On top of that, then, of course, we have the predicates. I have shown a couple of these predicates, indexing and spatial histograms, spatial temporal histograms to get the query optimizer, the cost for the query optimizer. So this is basically the architecture of MobilityDB, and then we launched MobilityDB 1.0 1 year ago in April, almost 2 years ago, or 1.5 years ago, and then suddenly it was quite successful. A lot of, in particular, Wendell, that is going to speak next, is using there for air traffic control in the US. But then we were asked more challenging scenarios. And then this is one challenging scenario. Currently, we were doing mobility analytics on historical data. We have MobilityDB on a database server, and we do all these nice queries on MobilityDB. But suppose we were working with the Brussels public transportation company, and then they said to us, but we need more. We need a stream processing system. We have the 2,000 positions, 2,000 vehicles of the public transportation, buses, tramways, metros, minivans, etc., that are continuously sending their position to the headquarters near downtown Brussels. And then, of course, they collect that with a buffer system. Typically, it's Apache Kafka for such a accumulation of observations. And then we need to exactly do the same processing, the same capabilities, but now not in a database server, but in a streaming environment. And this is where MIOS comes into place. And then if you remember well this slide, so the vertical bar here was Mobility 1.0, and then we certainly need to somehow extract this yellow horizontal bar here, in which we need to extract all what is essential for spatial manipulating moving types independently of PostgreSQL. So basically, we took that. Of course, all this part on top depends on PostgreSQL, but also we need to borrow the geometrical part of PostGIS and the alphanumeric part of PostgreSQL in order to be able to have exactly the same expression power as we have in MobilityDB in this C library, which is a very small C library, less than 3 megabytes that you put into memory, and you have exactly the same expression power as in MobilityDB. So that is for stream processing. But now, in the context of the European project, which is called MobiSpaces, we have pushed much further this architecture, because imagine we have ships into the Mediterranean that have not because they are far away, they are not connected to the shore, so they cannot have an equivalent air traffic controller saying where should we do in this situation. So basically, all the ships needs to cooperate with, among each other in an ad hoc network. And so therefore, exactly the same architecture you have in each chip. You have all this architecture in a Raspberry Pi. We are able to put both MIOS and MobilityDB on a Raspberry Pi. A chip receives the locations of the ships, other ships around them, and they can do this temporal distance example that you have seen in this slide before, to avoid any collision in the middle of a storm in the middle of the Mediterranean. So exactly the same architecture. You can have it on edge processing, on stream processing, on a database server, or in the cloud. In the cloud, we have imagine all the trajectory that we need to analyze. There's a huge amount of data that is involved in trajectory analytics or mobility analytics. So we need Citus, which is a well-known extension for PostgreSQL extension for distributing data. And then we have a coordinator and a set of workers that have a piece of the information, a piece of all the trajectories, and then we can do this into a distributed environment. We can have very nice animation. This is an animation which is based on pgtile server. Amazing work from Paul. This is a complex piece of what you are seeing here. It's a complex piece of architecture, because each of these ships that is moving is containing between 20 and 30,000 points. So we need to do a lot of tiling, a lot of Douglas-Poiker simplification to be able to smoothly produce a film. That means 24 frames per second in a smooth way when you zoom in or zoom out. But we need to do the same in QGIS. As you know, in QGIS, the only language that we can have is Python, and then we cannot afford to every 24 frames per second ask to PostGIS to compute the next frame. So we need to prefetch some data from the database and do all the computations in Python, and this is with PyMios. So basically, you have PyMios allow us to have, or Mios in general allow us to have a huge ecosystem, because basically we are able to wrap up Mios, which is the basic library of which MobilityDB is based, in many possible languages. So why Mios? Because of course everyone knows the great job Paul is doing in Geos, and basically we follow the same path, and then we say we can do exactly the same for the mobility data types. And of course, when you have a mobility data type, I need to clip, for example, a flight to one particular geometry. I need to, inside Mios, I call the geos function for intersecting, for example, a line string and a polygon. So in essence, Mios enables a single code base for manipulating moving features in multiple programming environments and languages. And we have a basic triad, which is Mios in C, MobilityDB, which is a small SQL wrapper around Mios, and PyMios, which is a small Python wrapper around Mios. And then we are currently developing all these other wrappers to be able to apply the same Douglas-Poiker, temporal Douglas-Poiker simplification in whatever is your favorite language that you would like to program it. And finally, my last slide is about another work that we are doing in the context of another European project, which is called Emeralds. As I mentioned at the beginning, we aim to be 100% conformant with the OGC standards. We have provided MFG JSON, which is the equivalent of GeoJSON, but for moving features. We are providing well-known text and well-known binary. Well-known binary is essential for environments such as the cloud, in which every worker needs to send some information for other workers, and the well-known binary is the more efficient format for doing that. And we are currently developing and moving feature APIs. You may remember one of the first speakers today may mention about these APIs that you can ask OpenSky pieces of their data. So we are doing exactly the same, but using the moving feature standard that is being developed currently at the OGC. And even within this OGC, MobilityDB uses an open source test bench for designing and implementing all these standards. So that concludes my talk. There is a lot of reference there, and many thanks for your attention. I open to your questions, happy to answer them.
All right, let's give people a chance to put their questions in the Q&A or in the chat. And I'll get after you first though, because I'm the host, I get to ask the first question. So you were around for Benjamin's talk, and I would describe that as like the first order database model for a trajectory, X, Y, maybe Z, and then a temporal, some sort of timestamp stuffed into the M. I wonder if you could like explain the limitations of that data model, like what you think is insufficient in that data model.
The idea is that as M is generic, the problem is that you cannot make assumptions on the order of the M's. And then, for example, in our case, M, we have a similar XYZ even for latitude, and then EM would be for time. But we are sure that we are ordered the time in order of arrival. And then when we are asking, as I mentioned, the trajectories typically are around 30,000 points. Mm-hmm. And then when we are asking what a particular position at a particular timestamp, you need to do sequential scan of all these 30,000 points. Now that I know that I are ordered in time, I do simply binary search to quickly go to this attribute. And even if the data is exactly stored the same, now MobilityDB know that they are ordered in time, and then I can do binary search.
Okay, so I'm going to come back at you again. You'll notice that there is actually a postgres function that will tell you whether your XYM data is a trajectory. It checks whether the M is monotonic, and if it is, it says, oh, that's a trajectory, or at least you can pretend it's a trajectory. And then Ben showed a couple of the trajectory functions we have, which are closest point of approach and distance at closest point, both of which are based on the incoming assumption that what you're handing it are trajectories, that is to say that the M is monotonic. What else is missing other than monotonicity?
If I may say, this is where we started at the beginning, and indeed there were, I don't know, 4 or 5 or 10, around 10 functions related to trajectory. MobilityDB has 1,000 functions for doing clipping, for doing add geometry. Add geometry is a nice function that Wendell will talk about. I need to clip a specific flight to a particular air traffic sector. So this is where we need to, of course, we take into account time, and then for this clipping, we call geos or polygons, depending on where you are asking este intersects or este intersection. Yeah. But basically, I need to ask as less time as possible, call geos I need to intelligently determine which timestamp I need to ask this information to polygons or to geos.
Okay, I got one other one, and I asked this question knowing full well that it's impossible to describe indexes in words, but can you describe for me spatial temporal indexing? Like, one of the things I found in spatial temporal indexing is because the X and Y's and Z's are in one metric space, and the time is in a completely different metric space, the indexes don't balance very well. They don't work nearly as well as when everything is in the same metric space. So I'm wondering, like, do you have a special sauce for spatial temporal indexing?
No, indeed, this you are talking about a very important part of our work. I must say that all the spatial indexing, as you mentioned, there is a spatial component and time component. We are borrowing your code for geographic or the grid all the grid that you are doing. You cannot do it better than us. So we borrow your code for this. We need to do the same for one-dimensional time spans, and then we inspired also from the TSTZ range and all the functions that are related to that, the statistics for TSTZ range. But then you need to combine both. You have two columns in the statistics for the space, and then two columns for the time, and then you need to combine both of that, and then you get the idea. It's just putting an n-dimensional way what you have already do in two dimensions.